Comes with block structured measure that is very useful to make meshes for simple geometries that could be easily reduced to hex blocks. The idea here is to quickly show you the capabilities of blockMesh utility in OpenFOAM. Let's dive into an example. In order to make block in blockMesh, certain conventions need to be followed. You can find more detail in the official documentation, but as a quick summary, if you have to make a block like this, you can start by defining the points which define the back plane, and then you can move to the front plane. And the first point will, for example, 0 point here, it will define the origin, and the point number 1 and the vector from point 0 to 1 will define first axis or x-axis in this case, and vector from point 1 to 2 will define y-axis, and 0, 1, 2 and 3 will define a plane which will be at third axis equal to 0, or in this case z equal to 0. And you need to follow right hand rule when you assemble these axes. Similarly, once you define this back plane, you can define the front plane, and again following the same convention, where you can start with the same ordering of points like 4, 5, 6 and 7. And once you define those points in an order, then you can simply call this function command, which basically lists all the points in an order, followed by the number of cells you want in one specific direction. For example, in this case, there are 3 cells along x direction, and then 1 in y direction and 1 in z direction. So we can quickly check how it works in OpenFOAM direct. So here I have a simple case. So you could see here we have set the vertices for in this blockMesh dict file, and in order to make a mesh, you simply have to go to the folder. For example, I am already in this directory, and then I can call the blockMesh by writing blockMesh, and if everything goes fine, you should not see any error message, and you see information like this. If we do not define anything for the boundaries, all the boundaries by default will be empty in OpenFOAM. So in order to define boundaries, we need a similar process. We need to define a type of the boundary. For example, here I have used wall. You can use patch or empty as well. And then you have to set the points for different faces. For example, I only want to contain faces which are defined by point 4, 7, 3 and 0. And in this case, the convention is that when looking from inside of the box, you should always follow a clockwise sense. And if we can check again here in our input file, that we have set here different boundaries for wall. If it is a wall boundary condition, anything other than wall should be patch. And then there is a specific boundary condition in OpenFOAM which is termed as empty, which is basically used to define 1D or 2D problems in OpenFOAM. By default, every mesh in OpenFOAM is 3-dimensional. And you can also see that in the output we have here different patches with different names here. Here, for example, we have shown an empty type of boundary condition where the top and bottom faces are defined as empty. This means that this is basically a one-dimensional problem, and the solver will ignore anything which is happening on those 2 faces. In order to quickly check if the mesh is right, we have several options. So we can start by using check mesh. So for example, if we write here check mesh, then we can see that everything is fine. But if you want to visualize the blocks itself, then you can use paraform.block, and that's very useful because in that sense you can see the vertex numbers. You can set the vertex number that you have set in the blockMesh dict file, and it's very useful for debugging purposes. You can also store the topology of the block to visualize it in Paraform or Paraview by using blockMesh and then block topology. This will basically write two files that you can visualize in Paraform. Again, we can see here, we can open those files, which basically shows the block topology that you can use to visualize the blocks in the mesh. It is very useful when you have multiple blocks and you can visualize this to check for different issues. And finally, you can just use directly Paraform to visualize the mesh, internal mesh. And here you can see that we have various options. You can load all the boundaries, and you can also load the internal mesh as shown here. For example, here you could see here you can color by different patches here, or you can only show here the internal mesh. And then if I go to internal mesh here, surface edges, we can see here different edges. We might want to visualize the points or nodes here, and we can also visualize these nodes or points here. So you can go to another view and then you can go to spreadsheet view. So you have the option to visualize point data. So if you click on a certain point, you can see that the point ID is 0. This is the ID that we set in blockMesh dict, and then this is highlighted here. And similarly, you can also visualize the cell data, and you can see that we have 3 cells in this mesh. You can also visualize the faces. It's a bit more complex, but the idea is that you can make a topodict file that I will show here. So if we go to this topodict file, we can process certain set of faces in OpenFOAM, and then we can export it as a VTK file. For example, if you want to visualize the faces, we can go here and write topo set, and then we have this face set f0 which has been defined, and then we can use form to VTK, and then we can use the face set and the name of face, and then it will store a file that we can again open on Paraview. For example, here I can go to this VTK folder, and then I can open this file, and if I then select only this file, for example, in the visualization browser here, we have those faces shown here, and then if I can then go here and select, so I can see that the face number 0 is in the middle, and then face number 2 is also an internal face. So we can visualize both here by setting the opacity of this value to something which is lower than 1. You could see those internal faces here, which you can color by face ID as well here. So this is the way that you can also visualize internal faces in blockMesh as well. And one last point is that Once you run this command, then the block mesh is written in this folder, which is called polymesh, and it contains the info about the points. So we have the 16 points in the mesh. Then we have a list where we can see for face number 0 here we have 4 points which are defining this face. So we have 16 faces, and on top of that we have an owner cell for each of the face, and similarly we have a neighbor cell only for internal faces. For example, we have for face 0 the neighbor cell index has index 1, and for face 1 the neighbor cell has an index of cell ID is 2, and these are most required for computing the flux in finite volume code. And similarly for the boundaries, the index of the face is used to define the boundaries. For example, for this left boundary we only have one face and it starts at index 2, and similarly for right it starts at index 3. So this is the way the mesh is stored in OpenFOAM. And we can also make even more complex meshes using blockMesh. And here, for example, you could see that if you have a surface, then you can project the vertices and the faces on a surface, like the one shown here. This is also taken from an example in OpenFOAM, and similarly, you can directly project edges on a certain face or object, and you can make even more complex meshes like this shown here.